Swayam Prabha. Digital India. Educated India.
With this lecture, let us begin the week 11 of the course. We shall be recapitulating the basics of high speed aerodynamics from an application perspective in this week. And today in this lecture, let us discuss about supersonic and hypersonic wind tunnel, some of the basic concepts. We recall having studied about the converging diverging nozzle, and wind tunnels are instruments where the converging diverging nozzle is an essential part. Wind tunnels create subsonic, supersonic and even hypersonic flows under controlled conditions in the laboratory, and for generating supersonic or hypersonic flow in the test section of a tunnel, the air or gas has to be expanded through the CD nozzle. We have the stagnation temperature and pressure respectively T naught and P naught, from where the expansion starts, and as the gas moves through the CD nozzle, the static properties, both temperature and pressure, they would be reducing. If it is a choked throat, then sonic condition is reached if it is an equilibrium flow at the throat of the CD nozzle. We call this as the throat area A star, and the test section area or the exit area is often referred to as AE, and the properties at the exit section or the test section are given by Mach number, temperature, pressure, etc., with the subscript E. We assume quasi one dimensional isentropic flow. Further, we assume calorically perfect gas, where continuity, momentum and energy equations are applied, and we end up getting a very important relation between the exit Mach number and the nozzle exit nozzle throat area ratio. This is something that we have learnt about, the area Mach number relation. We have made the simplifications or assumptions already mentioned in the previous slide. As you can understand, when those assumptions or simplifications are not fulfilled, then the solution, like the way we see it over here in the closed form, would not be possible anymore. How to solve such situations also we have discussed in some of the earlier lectures. So, we finally come up with this very important relation AE by A star whole square, which is expressed in terms of ME as well as gamma. Here of course, because of the calorically perfect gas assumption, gamma remains constant, and we find that the exit Mach number is simply a function of the exit to throat area ratio. We recall that since it is an isentropic expansion of the flow through the CD nozzle, the isentropic relations for pressure and temperature are valid. So, if you look at the pressure ratio, you find that again it is a function of ME and gamma. Same is the case for temperature, and you can easily plug in these relations and find the functional variations like the way we plotted it here. Further, the A by A star can also be seen over here, and all these are basically recapitulations of isentropic supersonic nozzle flow that we have learnt in a previous lecture. Now, with this theory in the background, if we think of creating a supersonic exit flow on one hand and a hypersonic exit flow on the other, that would give us some idea about the concerned numbers that are involved. So, these numbers give us some feeling of order of magnitude, and that is very important from an engineering perspective to be attained or acquired. So, to begin with, let us consider that in both cases the reservoir pressure and the temperature are both equal to standard atmospheric conditions. You know that in high pressure facilities this is not what we do usually. That means, if you really want to use atmospheric conditions in the reservoir, then you need to have much lower pressures in the downstream, so that the flow really expands to supersonic or hypersonic conditions under such a pressure gradient. On the other hand, if you are storing the gas in the reservoir at much elevated pressures or temperatures, then you may leave the gas to be expanded with atmospheric pressure in the downstream or at the exit end. So, that too would be discussed later, but to begin with, we are talking about a supersonic exit flow where the stagnation or reservoir conditions are as defined here. Now, plugging in the A by A star whole square relation into the equation we just recapitulated and substituting m is equal to 2, we consider the supersonic case as m e equal to 2, and that gives us a value of 2.85 for the area ratio square. If you take an under root, it gives you the A e by A star, which is 1.69, which means the exit area is 69% more than the throat area. As far as the temperature ratio is concerned, if you plug in the value of m e equal to 2, you find that the ratio gives you 1.8, which means the temperature at the exit will fall to 160 Kelvin. Similarly, pressure gives you a ratio of 7.82, which means the exit pressure needs to be 0.13 times atmosphere, which is of course subatmospheric and much lower pressure than atmospheric pressure. Now, when the expansion of the gas happens, water vapor contained in the air stored in the reservoir will condense as it expands through the CD nozzle to the exit area at 160 Kelvin. Water droplets would form a two phase flow in the test section. However, this can be prevented, and how do you prevent it? You use an air dryer upstream of the nozzle. So, if you typically look at a diagrammatic layout of an intermittent blow down type tunnel, then you might see the dryer mentioned over here. However, remember that there is a bit of a difference between the calculations that we are proceeding with currently and the tunnel that we are seeing over here in the sketch, because this is a high pressure tunnel where you exhaust the gas at 1 atm, which means the pressure in the reservoir is much higher than atmospheric pressure. But nevertheless, the dryer is indicated over here, and certain other important components are also visible, including the CD nozzle, the constant area test section and so on. The subatmospheric exit pressure of 0.13 atm is handled by designing the tunnel with a vacuum tank downstream of the diffuser section. This would easily provide the moderate pressure ratio to power the flow through the tunnel. Now, such kind of wind tunnels where you use subatmospheric conditions at the exit are called as in-draft tunnels. In-draft tunnels will definitely need subatmospheric conditions to be created at the exit, and therefore, a vacuum tank downstream of the diffuser section. That is important. So, the diffuser section is this that we are talking about. So, if you imagine that there was some kind of a vacuum tank here, which is maintained at subatmospheric pressure by running vacuum pumps, then you may leave the inlet of this tunnel open to atmosphere, and then it will suck air from the surrounding atmosphere and expand it to subatmospheric conditions, creating a supersonic flow as it moves through the test section. Now, this is typically a blow down supersonic wind tunnel, and it shows, the sketch shows the different components. You have a compressor over here, because you have to store pressure at elevated pressures much above atmospheric pressure. You have a storage tank where this high pressure air is stored, and before you get it to the storage tank, you dry it out. Then you allow the flow to move out into the tunnel as and when you need it, for which you operate the gate valve, the pressure regulator, then allow the flow to move into the wide angle diffuser, and then it starts expanding through the CD nozzle, creating the supersonic flow in the test section, and then it runs through a diffuser, a supersonic diffuser, before exhausting out of the tunnel at subsonic conditions. If higher pressures are required in the test section downstream of the nozzle exit, the reservoir air has to be pressurized above room conditions using an air compressor that we just saw a few minutes back. This compressed air can be stored in high pressure supply tanks before running the wind tunnel. In such a case, the wind tunnel is called as a blow down wind tunnel. There is of course no vacuum tank downstream of the exit of the tunnel, and the air usually flows into the atmosphere. So, we saw a variant of the one that we are calculating, and if you were to expand this idea a little further, we can think about different design possibilities of blow down type of a tunnel, where you are exhausting the gas into the atmosphere. You have a case where the nozzle is exhausting directly into the atmosphere without slowing it down to subsonic conditions. That means, you are essentially creating a supersonic open jet at atmospheric conditions, and you are placing a small model to be tested in that open jet. It forms a attached bow shock on the wedge model. You can imagine there is another situation over here which we call as the method B, where instead of a supersonic flow exhausting into the atmosphere, right at the exit you have a normal shock formed, and therefore, if you really want to do some testing with this tunnel, the model needs to be brought inside. Hopefully, here you will have a supersonic condition, and therefore, the shock will again form inside the model. There will be more complex interaction between the oblique shocks that are formed, which will reflect back from the walls, and then finally have some kind of an interaction with the normal shock that we see at the nozzle exit when no models are kept. So, we have called these two as method A and method B. Method A will need a higher stagnation pressure than method B, and also method C, which you will see in the next slide. So, the stagnation pressure requirement is the highest here. It is comparatively smaller in this case. So, if it is P naught A, then P naught A is greater than P naught B, and then we have a method C, where P naught C is lesser than P naught B is lesser than P naught A. This method has the constant area test section in which the wind tunnel model is placed, followed by a diffuser, which we call as the diffuser second throat, and you have a nozzle section here, you have a constant area test section here, and a diffuser section here, and we find that this kind of an arrangement will require the least amount of stagnation pressure to drive the tunnel. It creates a supersonic flow in the test section and then slows down the flow to subsonic condition through a series of oblique shocks before the flow exhausts into the atmosphere, which is more efficient than creating a strong normal shock at the exit of the test section, which is method B, and definitely further more advantageous and efficient than method A, which consumes the highest kind of power for running a facility like that, where you have an open jet at supersonic conditions. Here in this design, we progressively slow down the supersonic flow through a series of oblique shocks and finally turn it subsonic through a weak normal shock which forms at the end after the shock train, and therefore, because of the weak normal shock, lesser stagnation pressure loss is incurred than a strong single normal shock like we saw in method B, and this in turn leads to lower stagnation pressure requirement for performing the experiment. So, we also found a reason behind why the stagnation pressure requirement is far lesser in this case. When the shocks interact with the boundary layer formed on the walls of the wind tunnel, we know that there could be multiple shock wave boundary layer interactions, and they are also sources of losses in the flow, but nevertheless overall this method is turning out to be the most efficient. There could be another design variant which we call as closed return supersonic wind tunnel. These have been discussed in another course of mine, an NPTEL course, the fundamentals of theoretical and experimental aerodynamics, where you will have a more detailed description of the same. You can see that there is a difference over here compared to what we were discussing till now, that it is a closed circuit kind of a design, where the flow is recirculated, and every time that it returns from the downstream part of the wind tunnel test section, there are certain losses which have to be again made up by doing some more compressor work, and the flow also needs to be cooled before it is returned back to the main region of the wind tunnel, which is the working section or the test section where the wind tunnel model is inserted. Again, there is a dryer over here to remove possible accumulation of moisture and so on. So, this is another design variant that we are talking about. Now, we had a brief look at how things happen when we are looking at supersonic Mach numbers. Now, let us look at the hypersonic exit flow, where we choose a Mach number of 10 to do our calculations. We use the same equations that we used in the previous case, and if you substitute ME is equal to 10, then you find that the area ratio turns out to be quite significantly large. If you take a square root of that, the AE by A star is a huge number, 536, and of course, from here you can do some more calculations in order to work out some typical dimensions, which we will do in a later slide. Before we do that, we look at the temperature ratio, which becomes 21 in this case, and therefore, you can understand starting from 288 Kelvin, the T naught that we are talking about, if we expand it under these Mach 10 conditions, the exit temperature will be as low as 13.7 Kelvin, which is not far from absolute 0. So, the huge issue with this temperature, first of all, is that we will not be able to prevent liquefaction of air. So, that is a major impediment we have to work out. As far as pressure is concerned, we get a value of 4.24 into 10 to the power of 4 as the ratio, which means the pressure also drops to a very low value, much lower than atmospheric pressure. And then how do we handle these difficulties at Mach 10 conditions in a kind of situation like this, where we are expanding the flow from atmospheric conditions, is an issue. So, starting from the AE by A star ratio of 536, as I said a minute back, let us try to do some simple calculations to get an idea of the typical length scale of the nozzle. So, for doing that, of course, we need to imagine that there is some dimension at the exit, and we will consider a circular exit of diameter 25 centimeter, and then if we assume the throat also to be circular, then from this area ratio we can show that it is nothing but the ratio of square of the diameters, and from which you can work out the d star, which turns out to be 1.08 centimeters. So, it scales with the 25 at the exit, and it is a rather small throat that we are talking about. Comparing with the supersonic case, if the supersonic nozzle also had an exit dia of 25 centimeter, then with the supersonic case of ME equal to 2, the area ratio turning out to be 1.69 would give us a d star of 19 centimeter, which is much larger than the diameter that we are talking about over here. Now, a small throat diameter like the one we have calculated here is of course not a problem from a mechanical perspective, whether it is strength or its fabrication, but it is accompanied by some serious thermal problems, and that is our concern. The calculated temperature of the air at the nozzle exit for Mach 10 is 13.7 Kelvin, which is a very small temperature close to absolute 0, and the concern is that at 1 atm pressure air would liquefy at 81.6 Kelvin. Note that air liquefies at a higher temperature as the pressure increases, but in a hypersonic wind tunnel the pressure would be generally very low after the expansion through the CD nozzle has begun, and therefore, the temperature that it liquefies at is going to be low, but nevertheless this is an extremely low temperature that we are talking about, and therefore, inevitably the flow will encounter air liquefaction, which is going to be a severe problem to deal with. A two-phase flow, dry air and liquid air mixed, makes the aerodynamic data obtained from the tunnel absolutely non-usable, and therefore, the only way you can proceed at this point is that you must preheat the air to avoid air liquefaction during expansion through the CD nozzle for the conditions that we are trying to work out with. If we set the exit air temperature at the liquefaction temperature that we just talked about, which is nothing but 81.6 Kelvin at 1 atm pressure, the reservoir temperature must be heated to a value of about 1714 Kelvin, which purely comes from this temperature ratio and the minimum temperature that we are trying to achieve at the exit or the E section. So, this is the temperature of the air in the reservoir just to avoid air liquefaction, and electrical resistance coils in the reservoir can be used to create the above range of temperature. Resistance heaters can be designed to provide adequate heating even for continuous flow of hypersonic tunnels. Therefore, with electrical resistance coils you should be able to create continuous flow through a tunnel like this if you are looking for temperatures of this kind. However, if we want to replicate the atmospheric conditions at which this hypersonic flow would actually occur during flight of a hypersonic vehicle, then further heating may be required. So, now we are trying to connect with a hypersonic vehicle's flight conditions, and then you have to connect with the kind of temperatures which such a vehicle will encounter if you are trying to test it in a tunnel like this. Let us say at a standard altitude of about 59 kilometers, if we look at the temperature, the standard atmospheric temperature, that will be 256 Kelvin. To simulate that, we would need a T naught with the existing numbers of a huge number 5376 Kelvin, 5376 Kelvin, which is very difficult to obtain and store in the air tanks, which will be used for such a run. So, this again is a huge problem which will be difficult for us to achieve. In this context, it may be worthwhile to look at the nature of the standard atmosphere. You may recall that as you move along the altitude in terms of kilometers up from the surface of the earth, you are typically interested up to about 100 kilometers, up to which we have a sensible atmosphere. approximately, and we are talking about 59 kilometers altitude, which is somewhere here. And as you can see, the standard atmosphere is modeled this way with different gradient regions and isothermal regions. And then comes typical applications. This is taken from a publication of Ernst Heinrich Herschel from his book Basics of Aerothermodynamics, and we see a velocity altitude map for typical hypersonic flight vehicles. You have the altitude in kilometers along this direction and the velocity in kilometers per second along the x direction. And at an altitude of about 59 kilometers, you are talking about different kinds of operations which may involve both ascent as well as descent of such kind of vehicles. We have the re-entry vehicles, ascent and re-entry vehicles, cruise vehicles, as well as aero assisted orbital transfer vehicles, which are indicated in this diagram, along with some of the very important flow attributes at the different conditions in which they fly. So, we are not elaborating on that at this point, but we are just taking a quick glance of the range of possibilities which may occur for hypersonic missions. To recall the temperature that we had a look at in the previous slide, we left behind about a minute or two back. We said that resistance heaters are totally inadequate for reaching such temperatures, and to contain high pressure air at this temperature in any kind of storage vessel is again a serious materials problem, which means handling temperatures of this order is going to be a very difficult job. The nozzle throat size is relatively small. A nozzle throat of this small size will have a small transverse radius in the flow direction, and similar to the stagnation point heating at the nose of a blunt body, intense aerodynamic heating in the throat region can quickly erode the throat material and even destroy the integrity of the nozzle. So, we have an enormous aerodynamic heating coming up in such small throats, where a heating problem similar to stagnation point heating at the nose of blunt bodies do occur. Therefore, it is evident that like hypersonic vehicles, hypersonic wind tunnels and test facilities will also encounter serious high temperature and aerodynamic heating problems. Therefore, hypersonic test facilities are by default high temperature facilities. As far as the static pressure of the flow at the nozzle exit is concerned, that too is a very low pressure, and remember that we are talking about a P naught of 1 atm in this case. If we were talking about the 59 kilometer altitude condition, then like we saw the temperature, we should also look at the pressure. It turns out to be about 30 Newton per meter square, and since the atmospheric pressure at standard conditions is of the order of 10 to the power of 5 Newton per meter square, we can express the 59 kilometer altitude condition in terms of the standard atmosphere using this number. And in a Mach 10 hypersonic wind tunnel, to simulate the free stream pressure at 59 kilometers, which is about 30 pascals, the reservoir pressure must be increased. It must be jacked up, and we can show through this calculation that it should be about 12.3 atms. Only then, after expansion, would it reach the pressure of 59 kilometers altitude. So, to simulate Mach 10 flight at 59 kilometers, not only do we need to have a high reservoir temperature of more than 5000 Kelvin, but you also need a reservoir pressure of 12 atm or more. Everything else being equal, aerodynamic heating varies directly with the pressure. So, by increasing the reservoir pressure by this factor, the aforementioned reservoir and nozzle throat heat transfer problems are also exacerbated by the same factor, which means it becomes even more adverse, even more challenging. The above calculations have been made assuming a calorically perfect gas. Mind it, we are talking about extremely high temperatures, and if the stagnation reservoir temperature is of that order, more than 5000 Kelvin, air will certainly not behave as a calorically perfect one anymore. Almost all oxygen and substantial portion of the nitrogen in the air will be dissociated, and you have to consider it as a chemically reacting gas mixture. This reacting gas mixture under chemical equilibrium would expand to hypersonic velocity in the nozzle. So, the chemical equilibrium hopefully will be at the reservoir end, because it gets enough time of residence over there or relaxation time, so that it really reaches the equilibrium conditions. But as soon as it starts expanding through the hypersonic nozzle, we have serious doubt whether it will really remain that way. Portions of it may be frozen, portions of it may be non-equilibrium, and therefore, it is going to be a complicated flow as it moves through the nozzle. The thermodynamic state of air in a hypersonic tunnel has therefore to be carefully estimated, either through simulations or some empirical approach. The several problems associated with the continuous flow hypersonic tunnel, let us summarize them. For the design test section Mach number, the reservoir temperature must at the minimum be high enough to avoid air liquefaction in the test section, that is a basic minimum. In order to simulate the high enthalpy conditions encountered by the hypersonic flight vehicles in the atmosphere, the reservoir temperature must be considerably higher than that required just to avoid air liquefaction. So, we cited a case like that, where we tried to match up conditions at 59 kilometers altitude, and we saw a significantly higher temperature requirement at the stagnation end. It should be matching the standard atmosphere temperature corresponding to cruise or flight altitude of the concerned hypersonic vehicle, but it is really very difficult to achieve. In order to simulate the atmospheric pressure at various flight altitudes, the reservoir must be pressurized as well above 1 atmosphere. So, expanding from standard atmosphere condition to subatmospheric may not be the best choice. The combination of high pressure and high temperature in the reservoir, as well as small throat characteristic of hypersonic nozzles, gives rise to heat transfer problems in the nozzle throat, which becomes intense the longer the run time of the flow through the tunnel. This will aggravate the situation further. Then there is the materials problem of simply containing the hot high pressure gas for any length of time in the reservoir. So, there are multiple challenges to be faced. Let us conclude the lecture by saying that we had an introduction to supersonic and hypersonic wind tunnels with the basic concepts. We began with some of the knowledge that we had acquired in an earlier lecture. We looked at CD nozzle theory at that time, and in this lecture we tried to apply it to Mach 2 and Mach 10 condition, first by trying to expand the flow from atmospheric conditions to subatmospheric, and then trying to even match up conditions at a certain altitude of 59 kilometers to connect it with a practical application. Thank you.